learn Haskell the hard way. So what we'll be doing in this workshop is that we'll be going through an example application of how to build a real world Haskell application, which is going to be a CLI to the up developer API. Up developer.up. There we are.
In English, Poindexter.
Yes, and that will be recorded within the final results. So say what you will. But so yeah, with this, we're going to be building a client which can access this API to tell you what accounts you have, how much money you have, what your transaction history was. I didn't show that in the demo, but yeah, we'll be doing that as well. And this will go through a lot of the basics and intermediary stuff of Haskell, and just to understand exactly what a Haskell program is. If you want to follow along with this, you can check out Haskell Stack, which is a tool that installs the compiler for you. It's like the NPM for JavaScript or the Cargo for Rust or the things like that. So you can just install it via a simple script if you're on a Unix system, and there's installers if you're on Windows, and you can follow that path. So without further ado, we can probably get into it. And if you have any questions, feel free to ask them. For the first part, I've already coded this application and have the source code in front of me on another screen, so it might seem like I know a lot more than I actually do about Haskell. And for the second part, I might either take features or we can talk about the different features of Haskell. So first of all, this is just for my operating system. I'm going to start up a new project. So this makes Stack available for me. You can install Stack in your own ways, and we can create, up CLI. It's complaining that I don't have a up-to-date version of Stack. Don't really care. Up CLI. And then from there, I'm just going to get rid of my environment. So I've got this environment here. From there, I need to make sure that I can actually build this system. And from this up until a little while later is probably not something that you actually need to do. This is only so that I can make sure that my system builds because I've got a fancy computer. So I'm going to set, most of the time you can just write stack build and the system will build. CLI does equal the command line interface. And that's all you need. So right now, first of all, I'm in the package.yaml file. And the package.yaml file in a Stack project is where you write your dependencies. And also, like, you might have several executables to a project, and you might have a test suite and a library for these different projects. And then, so for the dependencies that we'll use for this is going to be rec, which is a request library for making HTTP requests, ASON, which is a JSON parsing library. We'll be using bytestring, which is how to handle strings of bytes that come from the internet, usually in requests. We'll be using lens, which I'm not going to explain, and maybe time if we get into it, although I don't think my version will include it, but I'll nevertheless put it in there. Beautiful. So this is not anything to do with what you'll need to do, but I'm just setting up an environment which will allow me
to have a SAM specific step.
Yeah, SAM specific. So I'm going to hpack and very SAM specific. And I'm going to copy my nvar_c. So dir_env is something that you definitely should check out, a SAM specific step, a triple S. Yes, very correct. This is a dir_env is something that you should check out. dir_env is really cool. It's a tool that allows you to specify different environments depending on what directory you're in. Particularly good for setting environment variables. Like currently, this one is set API up OAuth, which is my OAuth token, for which I'm not going to give you, but is going to be within an environment variable so that my program can access it. Nevertheless,
Is that a
Yeah.
GNU tool?
What, Darren?
base-
Yeah,
base
it might be a GNU tool, but I believe it probably does have support for Windows because it's a very widespread tool.
If I may interject,
Yes, go
was
for it.
a SAM-specific system setup step, which is rather serendipitous for us to see.
Yes, I hope you're enjoying it. So this, let's just get this running. So all I'm doing now is not really specific to you, but I'm setting up my build system so that it builds this basic project, which I'm not actually using Stack. I'm only using Cabal. So in Haskell, there are actually several build systems. So there's Stack, which can be is a dependency resolver, and what Stack allows you to do is expression does not evaluate to a derivation. Does it not? What do you mean it doesn't evaluate to a derivation? That's because it doesn't. There we are. So there are several build systems. At the very bottom level, there is GHC, and GHC stands for the Glasgow Haskell compiler, which is this one, GHC, and it is the compiler. It's like GCC for C code, and G++ for C++ code, or Clang or something. What don't you like currently?
Wait, it's Glaswegian.
Setup, segmentation fault. Great. Segmentation fault is really what I wanted. I think that the seg fault is not going to run again. Come on.
I don't know if I trust a Glaswegian compiler.
A Glaswegian compiler. Compiling lib, internal error, strange closure type. That is very, very scary. Beautiful.
You said the compiler was from Glasgow. A person from Glasgow is called a Glaswegian. And if the compiler is from Glasgow, most likely half the time it will compile, and the other half the time it will just leap out of your computer screen with a bottle, smash it over your head, and hurl a string of insults at you as a friendly greeting.
That sounds pretty accurate. Default.nix. So, okay, I can get around this because I don't actually really need Nix to build it. I just need the environment. Let's do that. Give me this end, and I should just be able to build it. No, because I haven't actually installed Cabal. So the next step above GHC is Cabal, and Cabal is the main build system. That's Cabal install, not Cabal to Nix. Cabal install. Cabal install allows you to create a larger project and collect all the files that are associated with that project and build it. So in here, the main file that is your Cabal file is upcli.cabal. So if you take a look inside that file, it's a custom syntax which contains all of the specification with how to build the test suite, the executable, and the library. And the executable and the library are different in that you can have one library that might be accessed by different executables. So for instance, I could have a library which has a command line interface and a web server and maybe some other thing. And that allows you to have multiple executables that are based off the same library in Stack. So let's see if I can actually build this correctly. Come on. Build, 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 build. Hey! So if I go Cabal up CLI exe, up to date. Cool. So now this just ran the code that we've got, and it's the current default code for Stack projects is just to print some func, and we'll go through that in a couple of seconds. The next layer up with these build systems is HPAC. Because nobody likes writing these up CLI files, someone developed a program called HPAC that allows you to write YAML files that this creates that Cabal file. I think I'm horrifying most people from Haskell, but whatever. So most of the time you'll be editing this file, which creates the Cabal file, and then stack allows you to help work out which packages will work together and sort of works as a wrapper to all the other tools. But nevertheless, that's your build systems. I use Nix. That's just because I'm on Nix OS, and you can look up Nix in your own time. It's a fantastic tool, but especially if you're on Unix. Nevertheless, now we can finally get into the code. Who wants to see some Haskell? No.
Woo!
Okay.
Me.
Woo!
That was
Sorry, is that a
scared people
delay
off already.
from unmute?
Is that what you were looking for?
Oh, maybe. I'm not sure at this point. Okay. Let's take a look at this. This is our first Haskell program that's created. What it does is it starts off in the app folder, which is there is a folder. This app folder is for the executable, and this source folder is for the library. So the idea is that all this folder does, the app thing is it's going to call the sumfunc function, and all the sumfunc function does is print it sumfunc. Now the thing is, as you may have noticed, there's no parentheses here, as you would normally. In Haskell, white space is function application, and you're going to have to get used to that. This is your main method as it is in a normal C program, and I just realized that in saying that, there is if I can quickly get SPL personal, not Haskell may, up CLI shell. Let's get the shell. There's a little bit of code that allows me to set up my editor integration nicely. So I'm just going to copy that over and use GHCIDE, which is, I need zlib, Haskell packages.ghcide. Beautiful. And now once I've done that, it should reload. This is direnv doing the automatic reloading of my environment. And it's using Nix. So it's just Nix installs these applications into my platform. So GHCIDE, it's just going to say not in scope. That's nasty. I don't know why. Oh, because I don't have doesn't know what type of project this is. So this is editor specific stuff. Hi allows me to specify what type of project this is. That and beautiful. It's probably just going to play about setup. Yay, and that's it. And this just sets GHCIDE is a language server which allows you to set up like editor integration so that it complains inside your editor whether something goes wrong. So now we're about to get serious. Proper code. Whew, good stuff. Just going to check it out in my other PC, what we've got. So what we're going to do is we're first going to realize here, we got two modules, module main where, module lib where. If you don't have these little, I've frozen. No, I'm back. Good. But my system's not back. Interesting. Up CLI. Come on. And if anyone's wondering what my editor is, it's NeoVim, and that's why it's got a little N in front of the Vim. That's not what I wanted. I wanted this. Okay, so we have modules. Module main is the main module, and it uses lib. And this is module lib, which has sumfunc inside the module, and import lib makes sumfunc available, which it calls. So I'm just going to call this to something a little bit more descriptive. So I'll just go run CLI, and we'll change this accordingly. We got here, it says not in scope sumfunc. Well, yes, you need to have it somewhere to export it. So we'll just do that. Beautiful. So first, I'm going to start writing some fun code. Let's just, for the starters, we're going to use do notation, and I'm not going to explain do notation because that would just take way too long. But it'll look like imperative code. It'll look like code that you're familiar with, but it really isn't. It's actually quite magical and interesting.
So basically, this is something that looks like what we're familiar with, but is actually completely different.
Yeah, so here we are. I've imported system.environment and allows me to get the args, which is the arguments to the function. I'm just going to save that. No, it doesn't like that. It should if I just run it again. Gonna work. There we go. So this just prints the arguments to the function. So we can just go like ping, boom. Look, that's it. From now on, we'll just be working in here. So this is like, okay, args is equal to the result of get args, sort of. Not really, but we'll get onto that. Then we can use lookup env to get the token that is in my environment, which I will not print for obvious reasons. And then I will go token m of, and this is a case expression. Now the case expression works sort of similar to what you'd expect in a normal switch case. Does everyone know what a switch case is?
Yes. They're also called select cases in some languages.
Yeah.
Or match statements in some. I think they're match statements in GDScript, right?
It's actually a bit closer to match as well, because you can do unwrapping.
Yeah, exactly. It is actually a lot closer.
I have no idea what that is.
Okay.
So the thing is, although yes, this is very similar to a case statement. This is like what lookup env does is that it says, okay, I want to see if can you find an API underscore up underscore OAuth thing, and if it's in there, it returns a maybe type. And the maybe type can either be just something or nothing. And this case allows you to expand between is it either just a token or is it nothing. So if it's nothing, the token wasn't found, and I can print expected to find API on up OAuth, and otherwise I'm just going to print found token. So,
sorry, where's the token variable? Like you said just token, but you used token m before that.
Yeah, so it says found token. So the token variable here, that's actually like declared. That's the declaration of the variable here.
Oh, okay.
Yeah.
So what would that be equal to the actual token value?
That's equal to the actual token as a string, and I'm not going to print it for obvious reasons.
Okay, cool.
Beautiful. So from there, we can start by actually using this token for something. So let's actually call another command with our token. So run command. Here's an interesting thing. If you have two arguments, it's just space. You have spaces for arguments, which is kind of weird. I like it. So I'm declaring a function here which takes two arguments. That's those two arguments. The first one with the string in the little brackets means array of strings, or list of strings, I should say, because it's not a fixed list thing. I'm going to talk a little bit about pattern matching at this point, which is quite exciting, and I'm very, very excited to look into it. So pattern matching is the idea that I can actually declare multiple definitions of this. So if I wanted to, I could declare this one. So put string line ping. Oh, actually, I should do pong, shouldn't I? Because it's pong. So what pattern matching does is that, like this is an example of pattern matching here, for which this itself is called this just token is called a pattern, in that this token has to be of a type just token. Yes, this is very true what Ewan said. And this nothing here is like if it's equal to nothing. Here you can do a lot more complicated stuff. So you can say, is it equal to a array with one element that's called ping, which is kind of cool. And if you wanted to, you can have like, arg here. Is it equal to an array with two elements for which the first one is ping, and then the second one is some sort of variable that you can use later. So pattern matching is one massive feature in Haskell that we can use. If an underscore, this is like underscore means we're not going to use the variable, and this will catch everything else. So if it doesn't catch on run a command, it'll catch on this second one, and it will print invalid command. So now if I just go ping, it should return me a pong. And if I do something that's like, I don't know, counts or something, it'll say invalid command. Beautiful. Beautiful. Okay, cool. So now let's actually do something relatively useful. We should probably actually ping something, shouldn't we?
We're doing something relatively useful. That would be a complete first.
Whoa, I know, right? So to do this, to be actually usually to do this, we're going to have to probably have some sort of method of calling the interwebs for the resource. Does everyone know who here is familiar with REST and how that works?
I mean, definitely not my brain when I'm trying to sleep at night.
I'm referring to REST as oh, it is in there. Are you not liking that? HPAC generated GHCID. Sorry, GHCID didn't think that I had a dependency on rec. So as of such, I will going to add that dependency so it does not complain. We'll just let it do that for a second. So for anyone who's not familiar with REST, REST is when you is a way of accessing resources that are on the internet, and very, very, very common, and it's used within your browsers. So there's several types of requests. We're only ever going to be using GET. And what GET requests do is that it's like, okay, I have a URL, get the resource at that URL. And getting the resource at that URL is exactly the same as you would when you would open that URL in a browser. So as of such, we're using rec to send a GET request to these URLs, which consist of the REST API endpoint. So let's take a look at if we take a look at the up API, we've got GET accounts. That's not the first one we're going to do. We're going to go, we're going to do the ping request here. Curl ping. Curl is a tool that allows you to ping from the command line, which is really cool for testing APIs, but we're not going to be using that right now. GHCIDE, come on. What else can I talk about? That's REST. Does anyone have any questions up at this point? Oh, you guys are a hard bunch. Indeed.
You're just really good at explaining, Sam, you know?
Oh, I'm just fantastic.
I have no idea what is happening and have not taken in anything for this entire session.
Beautiful. Okay, I'm just gonna start actually looking into developing some stuff right now while that is running, because GHCID, I think, is trying to get Cabal to install that. It's a bit bizarre because it is
Can you just run it with like run Haskell, or is that not work because of the dependencies?
It won't work because of the no, I don't think it will work because of the dependencies. Although I don't want to test that. I'm very much fine with just not having a working IDE integration and just coding for a couple of seconds. Okay. So let's create. My computer is getting slightly laggy.
Just waiting for you to print out your access token, by the way.
You're on there. Come on,
yeah.
Just ready to take that screenshot. Anyway, no, that's not the way that's not what we're going to do. So do notation again. It looks like imperative code. It's not imperative code. I might explain it a little bit later when we get into more fancy do notation. So I'm going to get rec.defaults. Actually, yeah.
Can explain what let syntax does if you use it? No.
Yeah, I'm not going to use it right now. I'm just going to, with options, I'm going to do it this way. Even though I haven't specified options yet, I'm just going to do it this way so that we can understand why I'm doing it. So options, we're going to hit the API endpoint. So up API endpoint is a string. So you'll notice here that I did on all my top level declarations, I put a type. And the thing is though, is that on almost nothing else do I put a type. There's no types on args, there's no type on token m, there's no types on just or anything else. I just only put them on the top level declarations. And the reason for that is that although Haskell is a strictly typed language, understand that it if you don't abide by its type systems, it will get very angry at you. So do so. But the thing is, in Haskell, these type declarations are actually optional. I could leave that out and it would work, and it wouldn't work, and it would work still just fine. And I could leave all the type declarations out. I could delete that one, I could delete that one, and it will just work. And the reason for that is that Haskell has something called type inference, where, for instance, here, if I have just token, right? Oh, let's even get a proper. What's a good example of type inference? We'll have some really good examples of type inference later. But it assumes it knows what the type is. So the fact that you're, it's basically JS. It is not basically JS. It is very bit different from JS, and I take an extraordinarily large offense to that. It's not dynamically typed. It's type inferred. Okay, cool. So next, what we're going to do is we're going to take in. I'm sorry to see you go, Kieran. If you are going, bye bye. I did not manage to say goodbye before he did. So I'm going to the options are what we're going to pass to the GET request, and there's nothing we need in the GET request except for one thing, which is, as they specify, we need to always pass in our access token under the authorization header and bearer with bearer before it. So that's the only difference we're going to make to our GET request. Otherwise, it's just a standard GET request with defaults, if I can speak. Man, my computer's getting quite slow. Authorization. So I'm going to add authorization. And this is weird lens stuff. There's a particular library that does. I need byte string actually. Hey, look, I actually did need byte string. Beautiful. I was wondering if I needed that, but I do.
You got a byte sting there, by the way.
Oh, do I have a byte sting? I do have a byte sting. Beautiful. Byte string. BS pack. Bearer. Token. So this says that I'm going to create an options with with a header named authorization, which has the value bearer ++, which is list concatenation in Haskell. And because strings are literally just arrays of chars in Haskell, that's exactly what they're defined to be, we can concatenate them. bs.pack packs it as a byte string, which allows it to be more easily sent over a network. This is Haskell. If you came into this workshop not knowing what this language is, you're in for something. This is learn Haskell the hard way. These operations that we're using with hang on if I can zip top. There's got these little dot tilde dot and those are part of the lens library, and lens is too complicated. I don't actually understand it entirely, but it's a really fancy way of accessing data structures that I honestly preferred this library didn't use. But nevertheless, I'm going to import those things from lens because we will need them. Another interesting thing is this $. So this $sign here is function application. So it's exactly the same as that, in that it evaluates the right-hand side and the left-hand side and applies the left-hand function to everything that's on the right-hand side of it. So, because if I didn't have this, the order of this evaluation would be I would pack the bearer into a byte string, and then I would add to the token. And now I don't actually have my GHC IDE for some reason. If I can please come back. Yes, it is exactly equivalent to that, as is shown. Ooh, keep on going. I believe in you. Wow. Cracky. Let's just keep going. We'll wait till that's done. That would bring up a type error. In fact, I could probably try and build it and it will yell at me. Maybe even for other reasons. I don't even know. Let's find out. Cabal is, GHC is very strict. Let's see if we can get this working. Oh, I'm actually understanding now. The reason why it's taking so long is that Cabal has never needed any of its dependencies to run. So the dependencies have not yet been installed yet. Understood. So as of such, we're coding blind. Let's do this. Anyway.
That's very like Haskell to load its dependencies lazily.
Well, it's not really loading its dependencies lazily. It wasn't installed because we hadn't written a program yet that actually uses any of the dependencies. And now I've got 3 dependencies, and nothing will run until it gets it there. Until that's done building. But nevertheless, that's our response. Now what are we going to do? We need to get the responses body. This is do notation, so I don't actually need the in. Let our body response rec.response body. I should probably comment some of these. So comment Haskell. In Haskell, block comments are like this. So this is run command runs the CLI command with argument and token. And similarly, line comments have 2 hyphens next to them. Have to get response, then get body. So that gets the response body, and return. Actually, am I going to return? I need to decode. Come on, That's just going, isn't it? Wow. Still requiring a little bit of time. Whatever. So the next thing we need to do after we've got the responses, we need to read it from the back. Hang on. We need to read it as JSON. So I'm going to install the ASON library, which is a Haskell library for JSON, and also import this operation, which will allow us to write our decoders later. Either decode our body. So what this does, this is where it gets really quite interesting. We've worked with a lot of interesting things. Like these are custom operators in Haskell. There's a lot of weird operators that can be defined as much as you want. We've done pattern matching. There's a little bit of type inference here and there. But this one is where it gets really quite interesting, where this is either decode. And what this does is it's going to decode the R body into a Haskell type. But the thing is, though, is that we're not actually, we haven't specified what we're decoding it into. So decoding, we need to transform into a Haskell type. So let's take a look at the response for this API endpoint. What have we got? We've got a meta, and we've got ID, and a status emoji. Cool. So to capture this in a Haskell data type, we need to create a Haskell data type for that. So let's do it. Yeah?
Before you go through the whole decoding, maybe you can just print out the JSON that comes in, just so we can see that before you
that's true. Although that being said, I'm literally waiting on this one because sadly, I can't build it or run it until that's done.
Oh, okay.
But yeah, it would be nice to do that. Let's see if we can. Oh, maybe I can just return or bs.put string line response body. Our body. Beautiful. Although I think that's a maybe. Is it a maybe? No, it's not. Come on, man.
Does it print out sending request after it sent the request, by the way?
It does. It does indeed.
Cool.
Okie dokie. So, I would like to do that. I'm just going to go on a little digression without actually seeing any running code, just so that we can have something fun to do while this is running. And that is to data types. And data types in Haskell are actually remarkably simple in comparison to other languages, because other ones like, oh, you have to make a class to make your own custom data type. In Haskell, it's like really, really, really simple. So to declare this data type, which could represent this ping, what do we have? We have a data ping response. And that declares a data type of ping response, which is equal to ping response meta. And I'll create a meta type. So this ping response only has one item in it. It's going to be called meta, and it has a data type. I'll create this in full. It's quite easy. Meta. So this is how you create data types in Haskell. They're pretty much one-liners. So the ping response contains, it's written twice, ping response, but it contains a meta. And the meta contains this record of things. So it contains an ID and a status. The reason why we write this twice is that this is technically called the constructor. So if we wanted to create an item, then we might go, I don't know, I'll go into that later, but this is data types. Does anyone have any questions in regards to what we've done so far? No. Beautiful. Wow. Again, incredibly unreasonably good. Very, very impressed. Crikey. You've learned something interesting now. I'm very, very happy that you have. And I've learned that GHC IDE takes a surprising amount of time to build these systems. So once this is done, we'll really be rocking, but whatever. I'm going to jump a little bit ahead just as
We can take some questions.
Oh, yeah. Are there any questions? Did I not catch any? Did I catch any?
Oh, no idea.
No. Yes. Beautiful. Okay. Maybe I should put some white space in here. That might be nice, just so that we can sending request. You got the options. Boom. Wonderful. So to make sure that we can decode this from JSON, what we need to do is we need to say that this, what we're going to do is we need to try and turn this JSON string that we get from the R body into one of these data types, so that it changes it from the JSON, the raw JSON structure, into a data type that we can work with. It's called marshalling the data types, I'm pretty sure. Yeah. So what we're going to do that, what we can say, we can give these data types what we call a type class. So that it's sort of like an interface in a sense, where we say that we know how to transfer this item from JSON. So this instantiates from JSON. So as of such, we have the from JSON method implemented within this data type. So it is sort of like an interface in Java, sort of, but a lot more powerful. So it requires, let's just do a quick implementation for this. Meta. Actually, do I like it that way? I want to put it down here. Do I like it? Yeah, let's do it that way. The ID. Let's do this. Look at this, more fancy operators. We have this operator, we have that operator, we have the $ again. Oof. These are all, you can define your own operators in Haskell, and the original creators of Haskell got a little bit excited with it. So there's quite a few.
By the way, you've got a just awesome 2 lines up from where you are.
Just awesome.
Just awesome. Pass just awesome.
Oh, just awesome. Indeed, I do have a just awesome. Just awesome. Beautiful. Okay, so this here implements passing JSON for the meta object. And all it does here, we say that pass JSON requires an object, so it's ASON with object, and we just give it a name so that if it fails, oh look, we're installing ASON now. We're getting closer. If we just give it a name so that if it fails, it actually knows what the name of the data type is, so that it can give you nice, pretty error messages. Then we have the $sign again. So the $sign is just to change the ordering of it. So everything after the $sign, which includes like all of these lines, is like the third argument to this with object. Anyone not worked with lambdas? Okay, I'm just going to give a quick explanation of what a lambda is, or an anonymous function. So so a lambda is a function, but it's declared inline. So this here is a function for which, like that, v. So this is a function which takes an argument v and returns this. And in functional programming, we often pass functions as arguments to other functions. TLS getting there. And this is what we're going to be doing here. And what this does here is a little bit of type class magic with functors and applicatives, but in the end, it's saying I have a meta object which requires a field of ID and status emoji, and then it automatically because we'll go into that later when we actually build the ping response one. So let's do ping response. I hope I have mortified you. Come on. There we are. With object. Yep, my computer system is going to crash. Sorry about that. There we are. Out of 10. Beautiful. This is what I want to hear. Let's see if I can actually get this to build properly. Come on. Consulting the cradle. We're up to lens, ASON. Oof. ASON's a tough one usually. It's a big library. Lens.
Can it do lots of different passing or something?
Honestly, I'm not 100% sure why it's so big. It's quite a simple library for what I'm using it for. Maybe it's just like touched a lot. Haskell has a lot of Haskell. I just found that when building ASON, that's the library that it crashes on.
Okay.
I might need a better computer for this sort of stuff. Whatever. Oh, look! Yes, I want to recover all my beautiful work that I just almost lost. So, here we are back. From JSON ping response. So this is implementing an interface, in a sense, the same way that you might do it in sort of implementing an interface, like in Java.
So Sam's created effectively a data type called ping response. And now he's implementing the ASIN.FromJSON interface for that ping response data type.
Exactly. And what's interesting about this is that I can go, okay, ping response contains it contains something in the meta. And because this meta item, it is a meta, Haskell knows how to decompile metas because I've declared it here. So as of such, all I need to do is specify that's a meta, and it'll sort of work. This sort of works in the same way because from JSON is implemented for strings as well. Come on, I am really egging on this because otherwise I get to write down absolutely everything, and it's just going to work first time, and I don't really want to do it that way. Nevertheless, let's just quickly. Okay, Is it all good now? Okay. Whew. Either decode our body. Come on. I need that to build because otherwise that's just going to keep crashing my PC. You can hear me, right?
We can hear you.
Yay. Cool. So then we're going to decode this and we're going to go right if it's this is right left. These are ethers. I'll explain ethers a little bit later. Response. And I can do some more fancy pattern matching. And we'll just put string line the status. And left error, put string line error. Okie dokie. So let's talk about this a little bit more. So what's particularly interesting about this is that we'll start off with either decode. Either decode returns an either, and an either is a data type which can either be left or it can be right. And usually, this is used in scenarios where you might go, it is right if you've managed to succeed, and it is left if it's an error. So as of such, either decode returns a data type that could represent either a failure or a success in passing this data type. So the right is that a success here, so it's got the ping response and it prints the status, and left is an error, for which you can print the error. And the fantastic thing about Haskell is that there are very little exceptions and all of that sort of stuff within the language, and it forces you to handle the other cases, because to be able to access this ping response, you have to come up with what happens if it is a left. Well, if it's a left, then I need to print an error, and that prevents you from writing programs that crash. It sort of forces you to do this. The second interesting thing about this is that I don't ever specify in either decode what type I'm going to decode to. What actually happens is that because I have said here that this here is of type ping response, it actually realizes that what? Please. Keep going. Okay. Whatever. Let's open that up again. Delete this one this time. Cool. So it actually realizes what it decodes it as from the type that you want here. So because it realizes that you want to write ping response. So because it realizes that you want something of type either, and the left is the string and the right is the ping response. Simply from the fact that you're calling these methods, you're expanding it in this way, it will decode it as a ping response. So it's really whack, and we'll see that we can actually do that in different ways later. So we can use the same method with no changes whatsoever, and just changes to the type, and it will actually do completely different things, which is incredible and lovely and amazing. But I don't really like going through the entire process of pinging something without actually seeing it run. So I want to see this happen. And it's taken a while. So, wow, why is GHC? I don't think it was doing this badly when, okay. Let's just do a Cabal build first. I'm just going to quickly check my personal version of this so that I can see if I've screwed up something. But I don't believe I have. Yeah, I have screwed something up. It's is here. That should be n dot. And then because of that, it's actually gonna, it doesn't need to compile all of the dependencies because it's already available in the environment. And there we are. Now GTID again. Woo! Okay. Sorry about that. That was my bad. I don't know why that should have come up with an error way before. Whatever. And we're going to get our errors. And I'll have it accessed within Haskell. There we are. Cool. So now if I reopen this and I get the environment back, I'll get the environment. Come on. Give it to me. There we are. Beautiful. So let's take a look at what our errors are. Expected to find ambiguous. Yeah. Okay. Fair enough. Who's got the Max? Can you turn down your? We can hear your background. Max.
Come on, Max.
Yeah, I've muted him. Cool.
Well,
So first of all, it's the first error is that ambiguous occurrence of put string line. That's because this byte string method also has a put string line, which allows you to print byte strings, which I'm not going to use. Interesting thing here, these strings, I'm going to use my first language extension. And this allows me to, because there are quite a few different string types within Haskell, for different purposes, overloaded strings. Oh, I need the $sign there. So here, this is the error, see? Cannot match expected type byte string with actual type char ++. So because we can't plus a byte string and a char because that evaluates as this plus the token. We need to have the $sign in there, and that fixes that, which is like I want to only turn this into a byte string, which is something gets into the network. Our body, obviously that's a mistype. Let's fix that. Cool. And that's it. Let's actually run this. Cabal run. Bing. No, it's not. Let's run the CLI. Da, 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 da. Boom. So let's actually take a look at a couple of things, because you said you wanted to see the response. Let's print the response. Buddy. Beautiful. So we'll also get the response as well. And it's not going to like that. Why not? Oh, because it's lazy. There we are. Okay, cool. So if we can actually print that, we're done. There. So we got the response. We have a meta and an ID and a status emoji. And we got that status emoji and we printed the status emoji, which is our first request. Oh, it's so fantastic. Isn't it a mess? Who wants to ask some questions in this breather now that we've got to this checkpoint? No? Yes? Okay, beautiful. The second thing, okay, the next thing that I'm going to do is that I'm going to clean this up a bit, because what we got args, get args, lookup end API, gets the token, passes the token onto command, sends the request, gets the body, decodes the body, and prints the status. Now, there's a lot of code in here that could be specific to up, like sending the request. So I'm just going to make a generic ping. So I'm just going to create a module. Of eerie silence. So IO, although I'm pretty much for this entire tutorial, I'm going to be using IO. IO is a type that allows you to declare side effects, which means that you can actually interact with the world. Any other type, you usually can't. You can only act like a pure mathematical function. So I'm just going to quickly ping response. Let's take, oh. I probably need the token. And we'll copy this over to here instead. Actually, I can just return this. Okay, I'll quickly, and we need these imports. Most of them rec, byte strings, control, lens, ASON. We need all of these over here. And overloaded strings. And the endpoint. And cool. And now from here, we can call our lib function, and it's a lot cleaner. So import system, import up. We qualified up as up. Up.ping response. I'll go through this. Up.meta. So this is another form of pattern matching. You can also pattern match when you're setting variables. So say for instance you have a deep structure like this, and you can go the result of this structure returns this up ping thing. But you can, if I want to, I can just declare it straight to ID and status. It's like breaking apart a JavaScript object, but a lot more powerful than that. So we're just going to put string line status and not require any of this anymore, but probably require exporting the meta. Up.meta, up.ping. What don't you like about up.ping? Oh, because it requires a token. That's why. And what did you like about this? Couldn't match either. Oh, it's an either. It is an either. That's very true. So I can't quite do that yet. So this is exactly the point. So here, it said could not match expected type either string ping response with actual type ping response. So the up.ping returns an either here, either string ping response, which means that I have to consider whether it is either a failure or a success. Otherwise, I'll just get a type error in which it'll say, hey, you haven't considered the left-hand side. So as of such, what I need to do is I need to actually write something that'll happen when the system fails, when you can't actually get access to it. So now I can just write up.ping response, up.meta, probably not going to use the ID, and we can just put string line status. And left error, we put string line the error.
Hey Sam, sorry to interrupt.
Yeah?
Did you see Daniel's question in the chat?
Oh, no, no, no,
I
no,
wasn't
no.
sure if you had already answered it.
Oh, I didn't. Sorry, pardon me. Let's take a look. What was the question?
It was.
I'm guessing.
I think it's a language extension.
Entirely different. Yeah. So these types of things, they're common white, and the reason why they are is that they're a language extension. So they actually change the way that your Haskell compiler tries to runs the Haskell code. So if I don't include that, it actually doesn't compile correctly. In fact, it should complain. Maybe it doesn't complain in this file anymore because it's not required. But let's take this one. Yeah, that one, it complains. And the reason why is that these types here, let's take a look at these. So they're CI byte string. So this is a particular type of string for which it's case insensitive, which is kind of cool. You can have very, very special types of strings. But usually we just like using these quotes to be able to get it to work. So as of such, I have the language here, overloaded strings, which means that I can just type a string and it'll turn into the type of string that it's expecting it to automatically. And that's not a default feature in Haskell, so we just added it at the top though. There, it's extraordinarily common though, so people just have it there. Thank you for pointing that out. Beautiful. I'm excited. We've got our IDE back. So let's take a look. We've done ping. Now we can probably do something a little bit more fun. Let's find out how much money I have, which you already know. But run command. So to run, let's do another. So say we're going to create another thing. We can go accounts here, and this says okay, if it doesn't match the ping, if it's one element and it just has accounts in it, then it'll match this one. So we can just go accounts token up.accounts, not in scope up.accounts, of course not, because we have not actually coded it yet. So let's code that properly. And there's not in scope, accounts, and let's code this. So the accounts function is actually quite similar to the ping function, because for the most part, what we're going to be doing is that we're going to be decoding it in some way. We're going to be sending a request to an API endpoint. It'll just be a different endpoint, because if we check a look at the we're gonna load it automatically for me. Oh, look at that. Instead of /util/ping, we'll have /accounts. Boom, get /accounts. There we are. So that's the different, and we're still gonna have the token. So it's almost exactly the same method, except for the only difference is actually this, where we're going to hit that endpoint. And as of such, we can set over a layer of abstraction here, and we can have something. We can pretty much call the same method from ping. We can extract this to quite an extreme extent. So I'm just going to show you what we're going to do. So we're going to go make request, the string, and then we're going to have the IO either string. And we're going to call this A, because we don't actually know what's going to return from this. Because in this one, it's a ping response, but the later one, we're not going to be able to work with a ping response for the accounts. We're going to need something a little bit more complicated than that, because we've got this monstrosity here. So as of such, I'm just going to leave that as A, which is something that you can do in Haskell. If you have a lowercase type there, it'll consider it a type variable. And particularly, it has to be a type variable for which I can change from JSON. So we're going to say from JSON A. Or actually, I won't put that yet, and we'll see what happens when we don't do that. So I'm just going to go URL do, and we're just going to copy all that over. Pretty much everything, except for maybe ++ URL instead. Now, you're complaining about something else probably. You're complaining about do. So now make request is just going to be, see you again. Have fun, whatever you're doing. Make request is going to be util/ping for ping. That's not there. Make request could not match expected. Yeah, cool. I'm just going to delete that then. We're going to talk a little bit about currying, either decode. Here we are. So this is saying no instance from JSON A arising from the use of either decode. So it's saying that what I don't know that I can actually decode to an A. An A is like a generic type in a function. It could be anything. So I need to specify that I can. So I'm just going to go from JSON A, ason.from JSON then. It should allow it. So this is fascinating here. Because here, make request util/ping, that's going to return a result. It's going to return a ping response and decode it as a ping response simply based off the fact that I've got that as a specified that as a type. That's all. In fact, we can create another thing. So we can go accounts. That was our other one. String IO. Either string counts response. Let's just go accounts. Obviously that doesn't exist yet. Accounts response equals, let's just do blank data type. Yeah, so right now it's complaining that make request isn't from JSON, and maybe I'll do generics. No, let's not do that. Should we just create a method? No, we won't do that yet. How am I going to tackle this? So the idea is here that we've got two functions. This is the ping function, and this is the accounts function. And that is the only difference between them, other than the fact that I need to specify how I'm going to decode the accounts. And the reason that we can do that is that the type that it's is decoded at is beautifully inferred. And another thing is that, coming back to light, I wanted to talk a little bit about, I'll talk about currying later. So I'll put the token there. Beautiful. Talk about currying. Let's define how to decode an accounts response. So what do we have for an accounts response? We have accounts. So in the accounts, there's a list of accounts. What's in the account? I care about the balance. How about the account name, which is, let's remove that. Account name, which is a string. Account balance, which is an amount. And then we'll have data account balance. In Haskell, all types have to be uppercase and all functions have to be lowercase, and there's nothing you can do about it. Sorry. So we've got the amount in base units there. Rip my lowercase types. Yep, you can't do it anymore. So it contains an account, it contains the account there and the amount. Beautiful. From here, it'll complain that from JSON isn't changeable from JSON. So we're gonna work through that a little bit and talk a lot. Yeah.
I think it could be good to cover currying because it's kind of applicable to lots of different scenarios, even outside of this program.
Yeah, I know. I'm going to do currying probably a little bit later on though, just so that I want to get two completely full done two decoders, and then I'll be able to compare how we can simplify those, which is kind of cool. And also I get to talk about monads here, like in a little bit more of a detailed sense. You ready?
Watch out for
that. Okay, accounts response. So the accounts response is quite easy. It contains a field named data. So pass JSON ason.with object, with object accounts response. Accounts response. We're going to take a data. Beautiful. So then it says, okay, sorry, like, yeah, we can do that, but I don't know how to decode an account. And yeah, that's fair enough. So we need to specify how to decode an account. And this is where it gets interesting and why I want to, where we're going to bring up monads. Because although this so far these decoders seem quite innocent, they're going to get not so innocent very soon. And the reason why is that if we keep going this, let's take a look at this data structure. This data structure here, this is we're at this level, right? So we've got the type, the ID, and the counts. However, I don't actually really care that much about the type because the type is going to always be an account because I'm hitting the accounts endpoint. And it says here, type of this resource, accounts, always will be. And I want to get this display name, which is actually within the attributes field. So what we're going to do is that we're going to use do notation. And this is a kind of a strange place to use it. So what we're going to do, we're going to use do notation and we're going to say accounts. We're going to get these attributes. Attributes equals v. And we're going to get the display name from the attributes, like so. And then we're going to get the balance. Oh, forgot to close my string. From the attributes. Beautiful. And then we're going to return the account with the display name and the balance. Yep, and now it's complaining that we don't have a from JSON for amount, which is fair enough. And defining that is really simple. So I might even just copy that and put it down here. Amount value in base units. Beautiful. What have we got? What are you complaining about? Because this is not an amount. There we are. Cool. So now it's all good. Here, this do notation block, because of the magic that occurs, this is actually sort of like an expression that's very similar to this. So you sort of consider this to be more of an expression type within a normal imperative language, and this to be more of an imperative, do one thing after the other and then make them all equal to each other. Do something at the end. However, in Haskell, the do notation is only a thin layer over the top of that. So what we're doing now is that, okay, we're going to get the attributes. We don't know what the attributes type is, but from the attributes, we can get the display name and the balance and just return that as part of it. This return wraps it in the parser object, actually, but I feel like I can't even explain it that much further than that. But nevertheless, we've got a count. And we've got the accounts. So let's take a look at my accounts. So we've got the accounts. No, it's not going to allow me. Let's just accounts, account response, account. Amount. Beautiful. Now it's going to complain. No. Yes, it's going to complain, but it's not actually going to show up. Beautiful. There we are. Up.accounts response, which contains the accounts object. And let's just print my accounts. That's not actually going to work because there's no thing for show, is there? Yeah, let's just instance show. Deriving show. No, for show amount. Yes, I know. So I'll derive that as well. Beautiful. Cabal run up CLI accounts. Okay. Let's do this. Let's run it and we'll talk about it. Because it's exciting. It's really exciting. Look at that. LD failed in exit status 1, undefined reference. What in the world is this? Monstrosity. Wow. CC failed. Let's just rebuild. Okay, now I'm not 100% sure. Undefined host name. Gosh. You shouldn't care about door. You don't need that cache. Gosh. A linker error is not something that you want to see during workshop, is it? Can I at least build or not? No. Wow! Too powerful. Just a new style, disk, fresh. Yes, friendly Haskell errors indeed. Gosh. Invar-C, higher license, readme. What if I do v1 build?
What's gone wrong with it? What's up?
For some reason, no, there's some sort of screwed up thing with the build system for which it's throwing a linker error. And it says CC, so it should never really undefined reference to blah-de-da-da closure. This is not one of my issues. It should never come up with an error like this because this is linking the application.
Yeah. Can you bypass Cabal and just use GHC or?
Not really, because Cabal does the dependency resolution.
Right. Or Stack
so
then?
I could try and use Stack, although Stack is going to take ages to install because Stack takes a very long time to install in the first time because it needs to install all of the dependencies manually.
Yeah, the GHC.
One by one. Oh, I think I got it. Oh no, I didn't.
Got it.
No. Wow, that would be a serious run to the ground for the very last moment. Maybe it's because, yeah, it's a generated up CLI Cabal. So that means that the Cabal up file isn't fully up to date in comparison to the package file. So if I do that, is it going to work? Oh, it did. It did work. Okay, let's do this. Hey, look at that. It's my accounts.
Oh, nice.
Is there way too much there? There is. There is way too much there. Let's clear that. Bye-bye.
It might just be me, but my screen shares. Like, it just looks like you're still at the CLI from before. Oh, no, that's there.
Beautiful. What I'm going to do is that it was somehow printing. It was printing the response, which happens in make request. Yes, I don't want it to do that because that might reveal things. So I'm just going to keep it like this. There we are. So I have an account, an array, and the account name is up account. It's got an amount, that much, and savings, which is this much, and in base units. And we have our data types, which is really cool. But what's really oh, hooray! I know. What's really cool about this is that we only ever, to define the two differences between these functions, we only ever change this type. The only difference is this type and that string. And Haskell is particularly good in being able to really highly abstract things to like a level that no other programming language I've seen at least can do, and reuse code really, really well. I'm going to talk a little bit about currying, and this is interesting. So I'm going to take a look first at this type signature here. Actually, let's take a look at the lib one. That might be a little bit more makes sense. You got a type signature here, run command. This says run command is a function which takes two arguments, a string array, and a string, and returns IO, which is to basically return something that does something, and does something, does something. But the interesting thing about this declaration is that there's not really a split between the arguments and the result. So this would be the result normally, and these two are the arguments. But you could easily think about this also as being a function which takes one argument and actually just returns like that. Returns another function which takes one argument and then returns the result. Now the thing is with Haskell is that compiled because they actually mean the same thing.
You might be able to do like a generic demo.
So
just to show that.
Yeah, I'm going to go back to source lib. So let's go to source up because that's got a really good example. So what's really cool about this is that, say, for instance, I've got here a function which takes a string, which is the URL and the endpoint, a string, which is the token, and returns the result, IOE the string A. And what I can do, if I wanted to, I can either in ping here, the bottom, I can call that, I can say token, and then pass the token and the string. But the thing is, if I wanted to, I could say that is equal to make request under one argument. And because I've done that, it only puts in one argument and it returns this value. It returns this function. And that function's type is the same as this function's type. And that allows us this is what's called currying and partial application. So partial application is applying only one of the a few of the function's arguments, and then passing around that function. And we can do that the same thing for the accounts. We can remove this token because that's the same thing and it's shorter. I guessed waiting in lobby. You are allowed in.
Thank you.
Hello. You managed to make it to the last 20 minutes of a Haskell workshop, and I would be very impressed whether you could follow up to this, because I don't think even the people who are following too much of it.
That's okay. I just want to get a sense of it, the vibe, you know.
The vibe. How's the vibe going, everyone?
We're vibing.
We're vibing?
Yeah.
Any other comments from people other than Ewan? Well, it's definitely a vibe, says Pendle.
That's good. That's good. Looks cool.
Beautiful. Okay, so now what I'm going to do is that one thing that we do care about usually with balances is that if I have multiple accounts, I probably want to know how much money I have in total. So we'll just go sum accounts. We'll define a function. The function takes a list of accounts and returns an integer which represents how much money is in the accounts in cents. Accounts equals da, da, da. Okay, now what we can do here is that Haskell is particularly known for its list functions because we don't actually have loops in Haskell. So to loop over this account, we have methods that map over it. So say, for instance, we do like maps and sum. So I'll give you an example of how to sum a list of accounts. So let's take a look at our account data type first. Source up account. Our account data type is that, and then our amount data type is down there. You can just see it. It's a little bit of hectic. There's an instance JSON in the way, but there it is there. So it has a name and a balance, and then the account has the amount in base units. So I'm just going to code this out because it's going to be, I want to talk about it a little bit later in full. Up dot amount in base units dot up dot account balance accounts, close parentheses. So it's not going to like that because it doesn't know what that is. So I'm going to specify that it's from the up module. Cool, and we're done. Beautiful. So this is how we get around not having loops in Haskell. We'll start from the inner part, and let's put a $sign there so that we don't have to use that parentheses. It's the same thing. So the $sign evaluates the right-hand side and completely, and then applies it to this function. It's the same as having the parentheses. So map, who has ever worked with map? Has anyone other than you worked with map? Map, reduce, and filter in JS and Python? Particularly JS?
Oh,
No?
yeah, we've got one.
You got one? Yeah, we got die. Beautiful. Okay, wonderful. So what a map does is that it very simply takes an array and it applies a function that you give it to every element in that array and then returns a new array. So say, for instance, if we wanted to if you wanted to get all of the accounts of the this is not gonna pass, obviously. But if you want all of the accounts of the all the balances of the accounts, then I would say, okay, apply the account balance function, and the account balance function is actually just a function which takes an account and returns the balance object. So it's a getter for the accounts. That's a function itself. It's not going to like this because it's saying that I can't add together accounts. I can only add together integers. So as of such, I want to get the up.account, amount in base units. You're gonna let me do that? Cool. The amount in base units of that function, and then it will compile. This here dot is function composition. Does anyone remember function composition from methods? No? Anyone? Yes? Beautiful. So the idea of function composition is that we take the function on the right-hand side, and the outputs of that, we put it in the inputs of the function on the left-hand side. So what that means is that the function takes in an account, it gets out the balance, and then after that, it goes through this function where this takes an amount, and then it returns the amount in base units, which is an integer. So as of such, we've managed to change this accounts array into an array of integers. So we could do, I don't know, let's have some fun. Let's go, account amounts equals in some account amounts. And if I wanted to, because I can say that this is an array of integers. And you can put type declarations wherever you want and in Haskell and leave them out if you want. This will ensure that no matter what, this is an array of integers. So I'm just going to say that is. And then the sum function takes an array of a number and then adds all those numbers up and then gives it out. So now that we've got that, we should be able to put string line. Yes, exactly. FOG is written as f.g in Haskell. So show some accounts accounts. And now you'll see how many cents of dollars are in my bank account. Judge as you wish. As you already have seen a couple of times before, but whatever. Linking. Yep, there we are. So that's the total. And there you have it. That was basic coding ping and accounts and a little bit of array functions and type classes, and currying, and way too much things. And I'm probably going to stop there because in 12 more minutes, I don't think I can cover enough interesting new things. But I'm very curious, if it's not a question, can I get some mics on? I would like to see what everyone thinks of this. My Teams is completely broken. Ouch. Oof.
Yeah, I can speak. I just can't see the screen.
Ah, no.
So it's been an interesting podcast.
It would be an interesting podcast. Oh my gosh, a Haskell tutorial just as audio. That would be terrible. Oof. So, as I said before, Haskell's impossible to learn in 2 hours. The reason why I've done most of this workshop is for other people to understand just how different Haskell is, but also sort of hopefully pique your curiosity into these types of languages, because languages like Haskell are particularly good. They're easy to test. They're a lot less prone to fail, and they're very, very, very scalable.
This has been a terrible example of less prone to fail, just for the record.
Oh, but those are just
fail for external reasons, admittedly.
Not for reasons entirely unrelated to Haskell. Every single one of those was a build system error.
Yeah, fair enough.
Yeah, and that was my bad. Entirely.
It is true though. Like, in theory, there will be almost no runtime errors.
The actual language has almost no runtime errors if you do it right.
Yeah.
There are some functions that you can use which are unsafe functions, but if you just avoid those functions, you're pretty much guaranteed to write programs that never fail.
Yeah.
And there are other languages like Elm, which are very similar, which you can use to build web applications that actually never fail because they don't have those functions that fail in them, which is really cool.
I was intrigued to see. I've just forgotten what it's called. WREC? QREC?
WREC.
Wait.
Yeah, rec.
Rec. Yeah.
Yeah.
It was interesting. I haven't seen that before in Haskell.
There's a lot of web libraries, obviously. This is the easiest one I could find. I wanted something simpler, but no, we got Lens. I don't like
it seems like there should be something easier, but hey.
Yeah, there should.
I guess you need to be able to create headers. So yeah.
There are lots and lots of different ways that people can code libraries. There's way too much flexibility in Haskell. That's a problem. I think, yes, exactly. There's a lot of different. It's a weird syntax, and I think that the syntax is also. It shows that it's different in a fundamental nature.
It's interesting because it's in some ways it's like the syntax is actually really simple. There's like very few rules to it. It's just that those rules are totally different to other imperative languages, and there's also heaps, like the standard library and all the different operators and functions you need to learn to just do the basics is quite a bit. But once you get past that, it's really flexible.
Awesome. And I reckon that's a beautiful thing to just, maybe I'll stop recording and might include this on the YouTube, TPC YouTube later. And we can talk about it a little bit now.